Yes. Yes, Sanvi, can you explain that how first carbon is chiral carbon? Write in comment box. How first carbon is chiral carbon? Yes, Dhruv. Hitanshi. Okay. Another question. See, in a first structure, if you see properly, your carbon 2, carbon 3 and carbon 4, they are chiral carbon. First carbon is not chiral because if you go for detailed structure of this carbon, then aldehyde group, here first carbon is forming one double bond with oxygen, one with hydrogen, one with OH and another one with hydrogen and another one with CHOH, right? This way this carbon is forming one double bond with oxygen. So as per this, if you see your carbon, first carbon, which is aldehyde carbon, is forming one double bond, and hence hybridization is not sp3 and that is sp2. Yes, Isha, now this is clear. So this carbon hybridization is sp2 and not sp3, and because of this is not chiral carbon. For chiral carbon, this must form all the four single bonds, and that too with different groups. Second carbon, if you see, forming one bond with CHO, another with OH and one with hydrogen, and third bond with whole this group. Same way, third carbon, if you see, here CHOH, CHO. On this side CHOH, CH2OH. Another side with hydrogen and fourth side with OH. Fourth carbon, one side H, another side OH, one side CH2OH and another side this huge group. So all the four groups attached to the carbon is different, and hence second carbon, third carbon and fourth carbon, all these three carbon atoms, they are chiral carbon. Same way here. Now as you are telling that first and third, they are isomers, so they are enantiomers, yes or no? First and third structure, whether they are enantiomers of each other, yes or no? 1 and 2, they are enantiomers. 3 and 4, they are enantiomers. 1 and 3, can I say them as enantiomers? No. Why no, Ash? He is correct. As per definition, what is enantiomer? Non-superimposable mirror images. These two structures, they are non-superimposable, but they are not mirror images, and so they are not enantiomers of each other. So what are they? So structure 1 and 3, they are isomers, but non-superimposable, not mirror images. Same way, if you compare 2 and 4, 2 and 3, 1 and 4, all these structures, they are isomers of each other, but they are non-superimposable and not mirror images, and these type of isomers, they are known as diastereomers. These type of compounds, they are known as diastereomers. So this is another type of optical isomerism, diastereomerism. Non-superimposable, not mirror images of each other. Is this clear to everyone? One more type of optical isomerism, that is meso compound. This is meso compound. Suppose if I have one compound CHO, CHO, CHOH, CHOH. If I plot one mirror, then CHO, COH, H, COH, H and CH. Again my structure 5 and 6, they are enantiomers. Even if I keep one mirror over here in the center, then you see carefully that this first part is mirror image of the second part. This first part is mirror image of the second part. If I have mirror over here, then this is the kind of arrangement I will get. So those compounds in which upper part is mirror image of the lower part, same way here also. Upper part is mirror image of the lower part. Those compounds, they are known as meso compound. Those type of compound, they are known as meso compound. So this is all about different type of optical isomerism, enantiomers, diastereomers and meso compound. So here this type of optical isomerism is complete, where we are discussing about enantiomers, diastereomers and meso compound. One another type of indication is there, which is capital D and capital L type of nomenclature, where we write capital D and capital M. While writing name of the compound, we use this symbol. Now this capital D and capital L has no any relationship with small d and small l. These are totally different from each other. Capital D and capital L and small d and small l, they are totally different from each other. There is no any relationship between these two. If my compound is dextro, then dextro compound may be D also, capital D also, maybe capital L also. How we are deciding whether the compound is dextro-rotatory or levo-rotatory? Write in the comment box fast. How we are deciding whether compound is dextro-rotatory or levo-rotatory? Write in comment box fast. Dextro right turn, yes Priyal, but to which, whom they turn right? What is the name of that experimental method? Yes, by passing PPL, correct. Method name is polarimetry. Method name is polarimetry. We are using polarimetry method, right? You people are correct. Through plain polarized light, we decide whether the compound is dextro-rotatory or levo-rotatory. Means by experimental method only we can decide whether my compound is small d or small l. While for deciding capital D and capital L, if I see structure of lactic acid, see here I have written structure of lactic acid, 2-hydroxypropanoic acid, right? To this compound, if I write this way, here in middle I have my carbon. Now 2-hydroxypropanoic acid. Suppose this is plus. What do you mean by plus? What do you mean by plus? What do you mean by this symbol plus? If I'm writing plus 2 hydroxypropanoic acid, does this indicate anything? Yes. What that indicate as per this study, if I'm writing plus, this means that my compound is dextrorotatory, which rotate plane of polarized light towards right side. So looking at the structure, I can't decide. Experimentally, I have already decided that this is plus compound. Same way, 2 hydroxypropanoic acid. Let me complete this. And COOH and CH3 is remaining. I have CH3 over here. Here I have hydrogen. If I keep one mirror in between, then this OH comes on this side, CH3, COOH and H. This is minus 2 hydroxy propanoic acid, right? The symbols I'm using, I'm just assuming. It's not I have find out by experimental method, right? Here I'm just assuming these symbols. So these symbols we find out experimentally. But when I have to see capital D, capital L, this we decide by position of hydroxyl group. This we decide by position of hydroxyl group. As in the first structure, hydroxyl group is present on right side. This is capital L. This is capital L. While in the second case, as this is present on left hand side, this is L. So this is how we decide whether the compound is capital D or capital L. If hydroxy group present on right hand side and if hydroxy group present on left hand side. So this is how we find out whether the compound is capital D, capital L and is not having any relationship with small d, small l. This concept is very much useful. In board exams, even in competitive exams, they ask number of questions from this topic. Optical activity, what is enantiomers, what is diastereomers, what is meso compound. One more term I want to clarify over here with you people, that is racemic mixture. If I have one sample, if 50% compound is dextrorotatory and if 50% compound is levorotatory, then that mixture is known as racemic mixture. To this even we represent by plus or minus dl. Right? Here I have 50% D compound, 50% L compound. Now this if rotate plane of polarized light towards the right side, 50% of compound, and another 50 is rotating towards the left side. My total rotation is 0, and so racemic mixtures are always optically inactive. Racemic mixtures are always optically inactive. That's okay. Whoever is logging from Gayatri Patel's account. Okay, Arya. You can see this video again. I'll upload this video. You can see again. Not to worry. So this is what is about racemic mixture. So hope all these things are very clear what I covered today. Here I'm ending my today's session. In the next session, that is on Tuesday, we'll discuss about chemical reactions of haloalkane haloarene compound. Till that, complete with the homework whichever I'm giving through WhatsApp group. Go through that. If any query, just tell me in WhatsApp separately, not in a group.